Okay, let's start with a number. 75 microns.
That's it. SS304L stainless steel foil. We're talking thinner than a human hair.
And it's critical stuff, for things like hydrogen fuel cell plates.
Absolutely. Which brings up a huge manufacturing problem. How do you cut something that delicate with precision, but without ruining the metal in the process?
And that's exactly what this 2026 study by Lin Wang's team looked into. They took 5 different machining methods and basically set them up for a battle royale.
It's a great premise. They wanted to know if how you cut the foil actually changes what the foil is, fundamentally.
So they pitted thermal methods like lasers and EDM against mechanical and chemical wars.
Right. Laser, EDM, mechanical milling, waterjet, and then photochemical etching, all in the ring together.
And the first result is, I think, a bit of a paradox. Let's talk about strength. You would assume, I would assume, that blasting the edge with water and abrasives or burning it with a laser would have to compromise the overall strength.
You'd think so, but the data just flat out disagrees. The yield stress, for example, it barely moved. Stayed right around 315 megapascals, no matter what they did.
And the ultimate tensile strength was the same story, locked in at around 700 MBT.
It makes a certain kind of sense, though, when you remember that strength is a bulk property.
Right. So you're pulling on the entire atomic structure. A few tiny defects on the very, very edge are just too small to change that global force you need to break the whole sample.
Exactly. They're just a drop in the bucket. But while they were all equally strong, they were definitely not all equally stretchy.
Oh, this is where it gets really interesting, the ductility.
It was night and day. Just a huge difference.
The winners, and let's call them that, were laser cutting and the photochemical etching.
Yeah, they stretched like crazy. They hit a strain of almost 0.79, and they failed right in the middle of the sample, which is what you want to see.
That's an intrinsic failure. The material itself gave out not the cut, but the losers.
The other three, yeah. Waterjet, EDM, and milling. They all failed way, way earlier.
And critically, they all failed, starting from the edges.
Right at the cut. Which brings us to what I think is the biggest trap here.
The smoothness trap, yes. Okay, so if I'm a quality engineer, I'm looking for a smooth edge. Smooth equals good, right?
That's the textbook answer, yeah. Low roughness should mean fewer places for a crack to start.
Well, the study found that mechanical milling produced the absolute smoothest edge, a roughness of just 1.7 microns. Visually, it was perfect.
Visually, yes, but functionally, it was brittle.
Why? What's going on there?
It's the hidden damage. The milling process, that physical shearing, it creates severe work hardening right at the edge.
So the edge is already stressed out and exhausted before you even start the pull test.
Precisely. It looks great, but metallurgically, it's a structural time bomb just waiting to go off.
Okay, so then you have the water jet, which, I think of water as being the gentle option compared to a laser.
Not when it's moving at nearly the speed of sound and full of abrasive particles. The waterjet was by far the worst performer.
It was so bad it actually broke a known rule of materials testing the size effect.
Yeah, that was significant. Normally, a wider sample has a lower chance of failing from an edge defect. It's just statistics.
But the damage from the waterjet, these deep micro cracks, it was so dominant it didn't matter how wide the sample was, it just died.
It killed the ductility every single time. And yet the laser, which literally creates a heat-affected zone by melting the metal.
It performed almost as well as the pristine chemical etching. That's the part that feels so counterintuitive.
It is. The laser creates a defect, this recast layer, for sure. But it seems to be a very stable, consistent defect. It actually resists cracking better than the mechanical trauma from the mill or the waterjet.
So what's the big takeaway then, for anyone listening who actually works with these metal foils?
It's simple. If you're trying to measure the true properties of the foil itself,
you have to use photochemical etching or, surprisingly, laser cutting to make your test samples.
Because if you use a waterjet or a mill, you are not measuring your material.
You're just measuring how bad your cutting process is.
You're creating false data. You might throw out a perfectly good batch of steel because your PET method was wrong.
It just shows a real blind spot we can have in engineering. We trust what we can see. An edge looks clean, it looks smooth, we sign off on it.
But this proves that a visually perfect surface can hide a fundamental weakness.
Which leaves us with a question for you to think about. If a smooth edge in manufacturing can actually be a structural weakness, what other visual quality checks in your own workflow might be giving you a false sense of security?
It's a good reason to always look a little deeper than just the surface.